Nuclear energy is one of the most powerful and environmentally clean sources of energy. But it has an Achilles heel: radioactive waste. You can't burn it. You can't dissolve it. You can't destroy it. The only solution is to isolate it securely. And not for 10 years, but for tens or even hundreds of thousands of years. Today, we'll show you how this can be done. Simply, reliably, efficiently, and permanently. We live in a world where nuclear technology is advancing rapidly. More and more countries are building nuclear power plants and using radionuclides in medicine, industry, and defense. As a result, the accumulation of radioactive waste is accelerating. This is no longer a local issue. It's a global problem that cannot be ignored. Where does this waste come from? From reactor operations, fuel reprocessing, isotope production, and dismantling of old facilities. Even medicine, PET scans, oncology, generates hundreds of cubic meters of low-level radioactive materials. All of this is radioactive waste, liquid and solid, with different activity classes and half-lives. So, what should we do with this waste? Over the years, some strange, even dangerous, ideas have been proposed. For example, sending it into space, pack it up and launch it into orbit. But one rocket failure would mean radioactive material released into the atmosphere of the entire planet. Another idea, buried at a depth of 1 kilometer. In theory, elegant. In practice, technically complex, extremely expensive, and not always safe. Germany's experience with the ASI-2 repository showed that. Their groundwater leaked into the mine where the waste was stored. Now they have to retrieve it. Instead of forever, it became remediation after 30 years. Today, we are not truly solving this problem. We're just postponing it. We store waste in temporary barrels, place it in concrete cubes, metal containers, interim storage sites. But all of it is temporary. We're passing the responsibility on to future generations. But radioactive waste is not garbage. It consists of long-lived, dangerous substances that must be isolated not for decades, but for millennia. This requires a system that is reliable, long-lasting, and scientifically predictable. Not temporary storage, but final isolation. Current solutions are only stopgap measures. Concrete and glass crack. Metal rusts. Containers are expensive and not eternal. Repositories are full and new facilities take decades to build. At the same time, operating costs are enormous. And the design life of most storage sites is just a few hundred years. Far too short when we're talking about isotopes with half-lives of tens of thousands of years. We need a different approach. Simple, scalable, monitorable, and most importantly, reliable for thousands of years. That approach exists. It's available. It's logical. And now, we're going to show you exactly how it works. Requirements for an ideal radioactive waste isolation system. So, what defines a good technology for isolating radioactive waste? It must meet 5 key criteria. Reliability, the ability to accurately predict the behavior of radionuclides over hundreds or even thousands of years. Stability, the materials used must resist degradation from water, temperature, radiation, or time. Affordability, the solution shouldn't require billions of dollars per site. Monitorability, the repository must remain accessible for inspection, maintenance, or upgrades if needed. Compliance with the Alera principle, as low as reasonably achievable. This international standard means radiation risks must be reduced as far as is reasonably practical, considering technology, cost, and common sense. We're not obligated to pursue the impossible, but we are obligated to choose a solution that offers the best balance of safety, cost, and practicality. And finally, it must be realistically implementable here and now. No need for ultra-deep shafts, billionaire visionaries, or international mega projects. When we're talking about isolation that must last for thousands of years, external barriers alone are not enough. What's needed is an engineered system where packages of lower activity waste become an additional barrier against radionuclide migration for the more hazardous, long-lived materials. This is known as the principle of nested containment, a key to solving the radioactive waste problem reliably and rationally. At the very center are the most dangerous long-lived radionuclides, encapsulated in cement blocks. Inside each block is a salt-containing cementitious matrix that chemically binds the radionuclides into insoluble, immobile forms. Surrounded by protective layers of glass, bentonite clay, and stainless steel, this is not just a cement block. It's a multi-component chemical trap designed to remain stable for millennia. Next come intermediate-level wastes, which surround the high-activity blocks and act as a physical shield and a chemical filter. They are no longer just waste. They become a functional part of the barrier system. The outermost layer consists of low-level radioactive waste. Like the other blocks, these are placed within interlayers of glass and bentonite clay, forming a massive structural shell that plays a dual role, providing mechanical stability and limiting radionuclide migration. This approach is especially effective due to the volume distribution of waste types. Long-lived high-level waste accounts for a very small portion. Intermediate-level waste is much more abundant, and low-level waste is produced in hundreds of times greater volume. This nested structure provides multi-barrier protection while keeping costs optimized and manageable. The entire repository is further protected by external layers: a bentonite seal, reinforced concrete, stainless steel sheeting, and, if needed, a natural geological formation, selected to serve as a passive environmental barrier. It's like a matryoshka doll. The closer you get to the center, the more dangerous the contents, and the more robust the containment layers around them. The outer layers pose no threat to the environment and shield the inner ones effectively. The danger is not just buried deep. It is distributed across layers, shielded and immobilized by multiple physical and chemical barriers. Each barrier has its own function. Physically contains the waste, chemically binds radionuclides, hydraulically blocks moisture migration, structurally reinforces the entire repository. This is not a theory. It's a scalable, controllable, real-world technology, ready to be implemented today. To isolate radioactive waste for thousands of years, we need materials that remain reliable and stable, resisting time, moisture, temperature, and radiation. In addition to the cement matrix that binds radionuclides, there are two other materials, proven by both nature and engineering practice: bentonite and glass. In our technology, glass is not used to immobilize radionuclides inside, but rather as a system of barriers protecting cement blocks from both inside and outside against leaching and radionuclide migration. We're talking about simple, affordable sodium-calcium silicate glass, essentially the kind used in ordinary windows. It forms a durable and long-lasting isolating layer. The diffusion coefficient of radionuclides through dense, amorphous glass is extremely low, in the range of 10 superscript 2 superscript 2 to 10 superscript 2 m superscript 2/s, making it a highly effective diffusion barrier. Even at elevated temperatures, diffusion in glass is very slow, and at room temperature, it's virtually negligible. Actual values depend on the glass composition, pH of the environment, moisture, and microfractures in the material. What does this mean in practice? If radionuclides are behind a 1 millimeter thick layer of glass, it could take tens of thousands of years for them to pass through it. The second material is bentonite clay. It plays a key role as an internal and external hydrobarrier and filter around the waste packages. When wetted, bentonite swells and seals everything it surrounds. It closes microfractures in the glass, blocks pores, and retains radionuclides via cation exchange mechanisms. This is a naturally altered, geologically mature material, which means it doesn't degrade over time. And even after millennia, it remains plastic and highly effective. Together, glass and bentonite form a dual protective barrier. Glass barely allows any radionuclides to pass, and bentonite heals cracks and binds a few radionuclides that might eventually migrate to the glass over millennia. And most importantly, both materials are inexpensive, widely available, easy to apply in field conditions, and resistant to aging. That's what makes them the foundation of a robust, predictable multi-barrier system, one that can be replicated, scaled, and built not in 100 years, but right now. How the proposed waste isolation technology works. What does this process look like in practice? Let's walk through the key steps of a real-world technology that transforms radioactive waste into a safe, stable, and long-lasting engineered structure. Step 1. Concentration of liquid radioactive waste. Everything begins with the processing of liquid radioactive waste, LRW. These wastes typically exist in large volumes, but contain relatively low concentrations of radioactive salts. To reduce volume and improve efficiency, we use drum film evaporators, specialized units that operate continuously without scale buildup and with low energy consumption. These systems concentrate the waste to a salt content of 700 to 800 grams per liter, roughly 20 times salter than seawater, which is ideal for subsequent cementation. Why is this important? The higher the concentration, the fewer cement blocks are needed, the smaller the storage facility, and the lower the total cost of long-term isolation. Step 2. Cementation and block formation. The concentrated solutions are mixed with a cementitious compound and poured into standardized steel molds. Each mold is pre-lined internally with layers of bentonite clay and glass, forming the first physical and chemical barriers. Once the mixture sets, the mold is sealed by welding, creating a hermetically sealed cement block, robust and protected from external influences. Each block is then certified and sent for interim storage for several years, during which time cement hydration occurs, reducing residual heat generation. Short-lived radionuclides decay, lowering overall activity. Internal chemical processes stabilize. Step 3. Layered placement and nested containment. A detailed database for each block is used to optimize logistics and define a precise placement strategy. During final placement, the nested containment principle is applied. The most active blocks are placed at the center. Blocks with lower activity are positioned closer to the outer layers. Between blocks and layers, additional bentonite and glass interlayers are inserted to enhance containment and separation. Placement is carried out by robotic systems, safely, accurately, and without human error. This results in a structural array where every block plays a role in the overall safety system. Step 4. Final sealing and protection. Once all blocks are in place, the entire repository is sealed using steel plates, reinforced concrete slabs, layers of clay, and other hydro-insulated materials, adapted to the site's specific geological and hydrological conditions. What we get is not just a storage site, but a final disposal facility, a long-term engineered structure designed to withstand moisture, temperature fluctuations, time, and even earthquakes. This system is logical, replicable, and verifiable. It allows us to treat radioactive waste not as a looming threat, but as an engineering challenge, one that can be solved responsibly, efficiently, and with foresight. A comparison with deep geological repositories. You often hear the phrase, radioactive waste must be buried as deep as possible. It sounds logical. The deeper, the safer. But let's take a closer look at what deep geological disposal actually involves. Deep repositories mean decades of design and regulatory approval, billions in construction costs, the need to locate unique geological formations, no access at all once the site is sealed, and a high cost of failure because nothing can be fixed afterward. On top of that, perpetual funding for monitoring and significant operational risk projected over thousands of years. Now, Let's look at the alternative. The nested isolation technology offers a near-surface facility, full access and monitoring. Even 500 years from now, no need for rare geological conditions. And modular design, build it where and when it's needed. And most importantly, everything is predictable. The migration of radionuclides through glass, bentonite, and cement composites has been studied, modeled, and verified in experiments. The barriers work. They can be seen, inspected, and maintained. And the cost? Much lower. No ultra-deep shafts. No multi-million-dollar infrastructure. This is not a mega project. It's an engineering solution, because depth alone is not a guarantee. Reliability comes from predictability, accessibility, and control. This technology is based on the use of standardized waste blocks. That means uniform shape and dimensions, automated production, precise placement without manual labor, minimal human error, and maximum reproducibility. A single block design can be used for intermediate level waste, low level waste, as well as irradiated filters and ion exchange resins. In current practice, a typical disposal container, such as the NZK 150, has a useful volume of less than 40% of its total capacity. However, when transferring waste to a licensed disposal operator, payment is required for the full container volume, which results in a significant cost. Additionally, the lifespan of such containers is limited: 50 years for interim storage, up to 250 years for near-surface or underground disposal, and only under ideal conditions, with no water ingress or chemical exposure. This means that within just 250 years, we'll once again face the question, what should be done with the waste inside these containers? In other words, the burden is passed on to future generations. In contrast, our proposed solution uses a standardized block, similar to a modular brick, which can be used to build containment structures of any configuration. Each block is not just a container, but an engineered element that plays an active role in the long-term isolation of radionuclides for thousands of years. These blocks are suitable for the safe disposal of high-level solid waste, filter materials, and limited quantities of ion exchange resins. It's important to note that this technology does not cover the disposal of actinides and transuranic elements, which are generated during spent nuclear fuel reprocessing. That is a separate and more specialized challenge. Nevertheless, this approach can be implemented in virtually any country, regardless of technical development level, and is well suited for the disposal of the majority of radioactive waste generated worldwide. Everything you've heard is real. This is not theory. It's not science fiction. This is an engineering solution ready for implementation. It's cheaper, it's simpler, it's predictable. It doesn't require centuries of maintenance, and it doesn't depend on deep boreholes or complex geology. The nested isolation technology is our chance to stop shifting the burden onto future generations. It's a way to do what needs to be done, reliably, effectively, and affordably. Support the development of this idea. Share it. Discuss it with your colleagues. Let's turn the problem of radioactive waste into an engineering task, not an environmental disaster.